All right, so we're going to solve exponential and logarithmic equations today. Let's start with exponential equations. And I'm going to start with really the easiest ones you might run across. Ones where you can make the bases match. So this is method one. This is trying to figure out a way to rewrite them so it's the same base on each side. So on this side I have base 2. It'd be really awesome if I could rewrite the right side to also have a base 2. Well, 16 is 2 to the 4th power. So the bases match. And think about it. If you have an equation and it's balanced and it's equal on each side, if the bases are the same, then those exponents have to be equal as well. On number 2, the bases are 27 and 9. So I want to have the same base. Think of a base that would work for both 27 and 9. So I'm thinking to myself, I know 9 is 3 squared. And I know this is 3 cubed. Now, I do have to remember a rule here, and it was when we have a power to a power. So like we had x squared cubed. Power to a power, you multiply. So I need to multiply this 3 times that entire exponent up there, that whole thing of x plus 3. So 3x plus 9. And this would be 2x minus 2 when I multiply that times the power. Since the bases match, the exponents must be equal, and I get x equals, what would that be? Minus 11. Okay, 8 and 4. Ooh, that's 2 cubed and 2 squared. So when I multiply those exponents, and then I can set those exponents equal to each other. Now the next examples, I really can't do that because I have 4 on this side and 15 on the other. I cannot make those bases match. Now there's technically 2 ways you could do this, so I will show both ways. One way is to just rewrite as a logarithm. If I rewrite as a logarithm, the base is 4, we're trying to get to 15, and a logarithm always equals the exponent. Well, technically, I'm done. There you go. Now, the other way you can do it is to take the log of both sides. Now, you say, well, that's crazy because the x is still in the exponent. But wait, no, it's not. Because when it's inside a logarithm, the exponent can move to the front and become a coefficient. Then all I'd have to do is divide. Now you may be thinking to yourself, listen, Britsky, you're crazy. Those are 2 totally different answers. No, they're not. If you remember our change of base formula, this was the way you could find that logarithm from a different calculator. So let me prove it. If I go in here and change that to a base 4 of 15, I get 1 point, I know you can't see that, but it's 1.95. If I put log of 15 divided by log of 4, I get 1.95. Get the same exact answer. So this is a way to prove that that change of base formula really is the same thing. I tend to go for the rewriting most of the time. There are times that you do have to take the log of both sides, but most of the time we can do it without. Okay, so if I rewrite this, I'd have log base 10 of 120,000 equals x. Technically, you're done. You can put it in the calculator to find the decimal, but this is the exact answer. Now, on this one, I have something next to my exponential. So I would need to move that first before I can rewrite it. On example 7, we have a 2 in front. Be careful. Some people try to multiply the 2 times the 10. You cannot do that because this 10 is being guarded by that exponent. The exponent's only being applied to the 10. The only way we can get rid of that 2 is to divide it from both sides. Now I can rewrite it. But this time I'm not done yet because there is something next to the x. So this time I'd go ahead and find log of 4,000. But then I'm going to need to add 1 to it. And I'm going to get the decimal, 4.602 equals x. All right, so undo addition and subtraction first. Undo multiplication. Now we're going to undo the exponents. And the way we undo an exponent is with a logarithm. Now remember, log base e, that looks like the word loads. We don't like it. That's an ln. So that would be on the calculator as an ln. So that would be ln of 6 equals 0.6x. We would have to find ln of 6 and then divide that by the coefficient of x. Now this last example for the exponentials, this one would be a bonus type problem. This would be one where I have to take the log of both sides. I'm going to put this one in a separate video. So this is going to be separate. If you are interested in a possible bonus question on the test, that will be in a video at the end. I wanted to go ahead and make sure I got to the logarithmic equations because we've been doing a lot of exponential. For a logarithmic equation, the best thing to do is to rewrite as an exponential. So the base is 4, exponent is 2, and we're trying to get to x plus 3. Well, 4 squared is 16, so x is 13. Now, I do have to check my answers. The argument of a logarithm, let's make a note of this, the argument must be greater than 0 every time. Well, if I plug in 13 here, I'm good. So we kind of want to make a mental note that we always want to check to make sure the argument is greater than 0. So example 12, I divided by the 3 first to isolate that logarithm. Now remember, ln is base e. So this is really e to the 4th equals 2x. So I'd find e to the fourth and divide by 2. And my argument's going to be positive. On 13, I have 2 logarithms. These are being added. So when we had 2 logarithms and they were being added, we condensed them using multiplication. So I'm going to multiply those 2 together. That would give me x squared minus 7x. Now I can rewrite. The base is 2, exponent is 3. Now this is a quadratic. I better set it equal to 0. So I would subtract the 8, so I have everything on one side, and then I'd pray that Miss Zembritsky gave me something that factors nice. And it does. So I have 2 answers for my x. But I want to double check. The argument must always be greater than 0. So if I plug in 8, I'm good. But if I plug in -1, I am not. So this one had an extraneous solution, one that did not work. Now in the last example, I have a logarithm equals a logarithm. Now notice the bases on these match. So remember what we talked about with exponentials. If the bases match and it's balanced, that means that those arguments must be equal. Now double check. Are my arguments going to be positive? They are.